Hi everybody, in this video I want to derive an expression for the electric potential difference developed between the ends of a neutral conductor moving perpendicular to a magnetic field. Alright, so let's imagine we have a magnetic field into the board. Our neutral conductor will be a neutral conducting bar of length L between the ends, and at this instant shown in the figure, the whole bar is moving to the left. Now, even though it's a neutral conductor, it's going to have both positive and negative charge, just in equal amounts. Now, the positive charge is all locked in place, locked with the nuclei, but some of the electrons will be free to move. That's what it means to have a conductor. So let's consider what happens to those free electrons as this bar moves to the left. If the bar is moving to the left, that means you have electrons moving with the bar to the left. Let's imagine the magnetic force on those electrons. So the magnetic force on a charge moving with velocity v in a magnetic field B is given by this cross product. So if we have the free electrons moving to the left with the bar, that's Q times V to the right. QV cross B gives us a force on those free electrons, a magnetic force toward the top of the bar. So the free electrons will migrate toward the top of the bar. As electrons move to the top of the bar, that leaves an excess of positive charge at the bottom of the bar. Now, free electrons will migrate up toward the top of the bar until we get so much excess negative charge up there that they repel further negative electrons that are trying to move up there. So really all these negatives want to repel themselves. It's just that they're driven up there by the magnetic force. So at some point, the magnetic force driving the electrons toward the top of the bar and the electrical repulsion of the electrons from each other will balance out. So we can consider that situation in more detail in order to find a quantitative expression for the difference in potential between the ends of the bar. We've already shown qualitatively that there'll be a potential difference here. If you have an excess of positive charge here, an excess of negative charge there, this will be a higher potential than this. But we can now quantify that. And we can do that by looking at by considering a free body diagram of the forces acting on one of these free electrons that would be free to move. So let's consider the free body diagram. So here's one of our free electrons. As discussed earlier, we've got a magnetic force toward the top of the bar. Now this is the vector expression for that magnetic force. Here's the magnitude of that magnetic force. Q, V, B, sine theta. Now, theta is the angle between the direction of the velocity and the magnetic field, 90 degrees in this case. So sine of theta is 1. Now, we need to quantify also the repulsion that one of the free electrons feels from all these other electrons. We can do that by thinking in terms of the electric field. So, due to this separation of negative and positive charge, there'll be an electric field developed in the bar that points this way. That electric field pointing up will exert forces on electrons toward the bottom of the bar. So we've got the electric force. The electric force on each of those electrons will have magnitude charge of the electron multiplied by the electric field. That electric field is due to this charge separation that's been happened as a result of the magnetic forces that we looked at earlier. All right, so as I was saying earlier, the magnetic force will drive free electrons toward the top of the bar up until that upward magnetic force is balanced by the downward repulsion on each electron. So that is, we'll get more and more charge, negative charge piling up here, excess of positive charge down here, until these two forces are in balance. All right, so our condition for that then is when those are in balance. So this will be equal in magnitude to that. Now, it's the same charge in both cases, so basically we have a situation that the electric field that is developed in the bar in response to the situation is equal to the speed the bar is moving multiplied by the strength of the magnetic field. And that's, of course, in the situation where the bar is moving perpendicular to the magnetic field. Now, we can relate the electric field in the bar to an electric potential difference between the ends by remembering that electric field, while often we think of it as something in newtons per coulomb, it's also something that has units of volts per meter. Electric field is the rate that electric potential is decreasing with distance. So I could multiply electric field strength by my incremental change in location and get the change in electric potential. Or I can then rearrange it this way and think in terms of absolute values. Instead of looking at little increments, I can look at more discrete lengths. So my change in electric potential in volts will be the electric field in volts per meter multiplied by my length in meters, assuming I've got a uniform electric field, which we'll assume is the case in here. So I'm going to multiply both sides of this equation by the length of the bar. And finally, the electric field in volts per meter multiplied by the length of the bar in meters, that would give me the difference in electric potential in volts. And so the induced electric potential difference between the ends of the bar in this situation will be equal to the speed the bar is moving multiplied by the strength of the magnetic field multiplied by the length of the bar. And this, of course, assuming that the bar is moving perpendicular to the magnetic field.